Yeah, thank you very much for the introduction. My talk is about learned cone beam CT reconstruction using neural ordinary differential equations. And now throughout this talk, we will be looking at this walnut data a lot. And if you go and you acquire cone beam CT projections at 3 circular trajectories at different heights of the walnut, and then you run an iterative reconstruction algorithm, you end up with a very nice reconstruction of the interior of the walnut. However, if you only sample the central circular trajectory of these different trajectories and you run the same reconstruction algorithm, you can already see some increased noise, and also you get some cone beam artifacts at the top and the bottom of the walnut. So sometimes you might be even more restricted and you are not able to densely sample even that single circular trajectory, but you might only be able to sample a subset of only few projection images. And then what you can see, if you again run the same reconstruction algorithm, you would just end up with a very noisy reconstruction. So what could we do about it? We could add a total variation regularizer to the iterative reconstruction algorithm. And then you can see that the noise is largely removed. However, you still have some cone beam artifacts at the top and the bottom of the walnut. And you also sometimes get some patchy behavior in the interior. So now the question is, can we find a better regularizer for that than the handcrafted TV one? And now if you look into the literature, what people often do in order to improve upon handcrafted regularization is they use method called, or that we can call, learned iterative reconstruction using unrolled networks. And the recipe for this method is usually the following. It's first, you get yourself inspired by some classical iterative reconstruction algorithm, and then you translate that into a neural network architecture by unrolling a fixed number of iterations of this algorithm in depth. And then what you do is you replace some of the components of this algorithm by a learnable counterpart. And typically, these components that you want to replace are those components that are related to regularization. And then you simply go and train your network end to end. Now, the problem with this is that these approaches are usually only applied to 2D data. And the reason why this cannot straightforward be applied to 3D data is that when you train this network end-to-end, what you need to do is you need to store your intermediate representation throughout all your unrolled iterations in order to compute a loss at the end, and then backpropagate that information into your learnable weights. So this just needs a lot of memory during training if you were to apply this to the 3D data as we have it in this case. So the question that we would like to ask in this talk is, can we find a method that helps us to reduce the required GPU memory so that we can actually train such a method on our 3D cone beam data? So this is the problem setting that we're looking at. The input to our reconstruction is an undersampled sinogram consisting only of 120 projection images along the single circular trajectory that I showed previously. And then we would like to apply our algorithm, and the target or the ground truth that we take at which we would like to arrive. Oh, it's not actually playing. Sorry. Yeah, okay. So I'm sorry. This should actually be a video on the right. That is a reconstruction computed from all the 3 different circular trajectories at the 3 different heights, where each of them is sampled by 1,200 projection images. All right, so if we look at related work, which is trying to apply such methods to 3D data, there have been a number of methods proposed. The first one that I would like to mention is that you could go and just train your unrolled iterations greedily, however, that or independently of each other. However, that probably doesn't lead to an optimal joint weight configuration for all the iterations. Then there was also a multi-scale reconstruction approach proposed, where they basically increased the resolution of the reconstruction with the number of iterations. And only the very last iteration is computed on the full resolution. And then recently there have been a number of methods proposed which use invertible networks for this task, because the advantage that you get here is that you do not need to store any intermediate representations at all, because you can basically recover all activations during your backward pass using invertible operations. So in this talk, we would like to look at yet another method to reduce the memory in this task. And we start by looking at this very simple target function, where we would like to find the reconstructed volume X, which minimizes this function, which is the sum of a data consistency term, measuring the forward projection of the current estimate of the volume. So A is the forward projection operator, and the actually measured projections. And as we're operating in a very IPUS problem, we are adding a regularizer to it. Now we can solve this iteratively using gradient descent. And given the current estimate of the volume, we arrive at the next estimate of the volume xn+1 by simply applying a step in the negative gradient direction. And here again, the gradient is composed of the gradient of the data consistency term on the one hand in gray, and then the gradient of the regularizer. And as I said before, what we would like to have is a trainable regularizer. So what we do here is we simply replace the gradient of the regularizer by a trainable network, in our case, just a unit parameterized by some parameters theta. And now if we follow the classical unrolling approach, we could go ahead and just unroll this equation over n iterations, and we would end up with something like here on the right, where basically given one estimate of the volume X, we apply two branches, one being the gradient of the data consistency term, and one being the gradient of the regularizer parameterized by the unit. Now, if you look at this function in the lower left again, so now all what we do is we simply get rid of this discrete sum that is summing up over the unrolled iterations. And instead, we formulate this as a kind of continuous formulation. So what happens is the sum is simply replaced by an integral, which integrates our problem from some time point 0 to some time point t. And the function that we're integrating this f of theta is basically still the same. So it still consists of basically the negative gradient of our problem target function. And now this equation with the integral in it is essentially nothing else than the solution to the following ordinary differential equation, where all we know about our reconstructed volume, which is now simply a function of this continuous variable t, is we know some initial condition, so some x0, and we know its temporal derivative being parameterized by this network. So if we now take this and translate it into a neural network architecture, we end up with what you can see here on the right. So let's look at this a little bit more in detail. What do we have here? So first we have the actual network that in this case, it's still the same network that has been like the residual branch in the classical unrolled version that I showed previously. And in this case, this is simply a network parameterizing the temporal derivative of our problem. Then we have the initial estimate of our volume, which is x0, and we simply use an FDK reconstruction for that. Then what we would like to get is this x star, which is hopefully an improvement over our initial FDK reconstruction. And all of this is happening in some magic or ordinary differential equation solver. So these solvers have been proposed in 2018 by Chen et al. In a paper called Neural Ordinary Differential Equations. And basically what the solver does is during the forward pass, it simply solves the given ordinary differential equation using numerical integration. And now the trick is during the backward pass, because in order to compute the gradients with respect to our free parameters in the backward pass, we do not need to do backpropagation through the internals of the solver. Instead, we use what they call the adjoint method in order to compute the gradients. And what this basically is doing is it computes the gradients by solving another ordinary differential equation backwards in time. I will not go into the specifics here now, but the important thing is we do not need to store our intermediate representations in the solver because we do not need to do classical backpropagation through the internals of the solver. And this basically saves us a lot of memory, which is nice. How can we train such a network? We use a volume size of 251 voxels cubic. And as I said previously, the input to our network are the 120 projection images over the full rotation. We have 41 different walnut scans, which we split into 33 for train and 4 for validation and testing each. We pick a fourth order Runge-Kutta solver for our integration and let it integrate our problem from some time point 0 to some time point 1 in 20 fixed sized steps. As I said before, the gradient of our regularizer is parameterized by unit, which is a 3D unit with 3 downsampling stages and 64 feature maps in the bottleneck. And finally, we optimize our network's weights by or using an SGD optimizer with momentum and learning rate 1. And the loss function is an L1 loss evaluated on the reconstructed volume, but only within the valid field of view, which you can see here on the right. Sorry. Okay, so as I said, we initialize our method with an FDK reconstruction, which does not really perform so well in this task, which is to be expected in this very ill-posed problem setting. And you can see it shows a lot of noise and streaks in the interior of the walnut, and also cone beam artifacts at the top and the bottom. We also compare to 2 classical iterative reconstruction methods, one being the SIRT, which is doing a pretty good job in removing or not producing so heavy cone beam artifacts, but is still very noisy. And then a TV regularized reconstruction, which, as I said previously, it is producing much smoother results, but still we have a lot of cone beam artifacts here. Then we also have one of the invertible network approaches, which I mentioned previously. And this one is doing a pretty good job in removing the cone beam artifacts. However, some noise pattern remains in the inside of the walnut. And then finally, our method is kind of achieving both removing the cone beam artifacts at the top and the bottom of the walnut, as well as largely removing the noise and the streaks in the interior of the walnut. This is also represented in the quantitative results, where the FDK reconstruction performs worse concerning all the 3 metrics, which is to be expected, followed by the 2 classical, not learning-based iterative approaches, and then both of the learning-based approaches work best, where our method even outperforms the invertible method on this problem setting and this data set. As I said, the main goal of this method was to reduce the memory needed to train such a method. And what you can see here in this plot is you can see the memory needed for training as well as inference, depending on the volume size of the reconstructed volume, where the point that we are currently operating at is highlighted by this gray dashed line. And you can see that we are able to train this method using something like 16 gigabytes of GPU memory. And during inference, we need something like 6-7 gigabytes of memory, which is nice because this is feasible on recent consumer graphics cards and is about an order of magnitude lower than what we would need if we would simply do the classical unrolling approach. The memory that we still see here stems from the fact that we still need to store a single forward and backward call to the network, but what we do not need is a forward and backward call to the entire chain of unrolled iterations. So that means that our memory consumption is basically independent of the integration bounds that we choose and of the number of update steps on the volume. And this also doesn't play, that is okay. So this already brings me to the last slide of my presentation. So we propose a method where the memory needed for training is independent of the number of update steps that you take on your volume. And that makes it possible to train such a network with learned regularization and data consistency at the same time on recent consumer graphics boards. As we use the same parameterization for all the time steps in our method, we do not have an explicit time-dependent behavior of our network that parameterizes the temporal derivative. And as we are using this trick of using the adjoint method for gradient computation, we achieve our reduction in memory by trading for a little bit increased computational load than what would be needed for classical backpropagation. And with that, I would like to thank you for your attention.
So we have time for maybe one question.
This was very interesting. I was wondering, is there like maybe a physics motivation for the ODE, or is it purely mathematical? And then I was wondering whether you've compared it to just a small scale unrolling scheme versus this new scheme.
Okay, so for your first question, which is whether there is a physics background basically or physics-based motivation to this, is kind of no. I mean, so the time parameter doesn't really mean time in this context, right? It's just some continuous variable that we integrate over. So not like other problems where time has a special meaning in the modeling context. So in that sense, yes, it's more like a mathematical motivation that you can, you know, if you do the residual updates, it's basically the same. If you take very small steps, you essentially arrive at something like the derivative. And the second, what was the second question again?
Have you compared to just a
yeah, sorry, no, sorry, but that's a very, very good point. Yeah, just reducing the size and the number of iterates so much that you can actually fit it on some graphics card and try it out and compare it to yeah, that's definitely something I'm planning to do in the future.
Yeah, so thank you. So let's start the speaker again.